Good afternoon, everyone. Welcome all to the afternoon session, like the day one afternoon session of the 1 week webinars. I hope we all had a very good, interaction, and we could listen to the wonderful thoughts or the inputs given by the stalwarts of the antenna domain. So now we have Dr.Swetha Amit as the resource person for the afternoon session, and I'm very happy to introduce her. I'll just try to quickly read out a brief profile. Professor Swetha Amit received her PhD in Electronics Engineering from Jain University, Bangalore in 2018. She did her ME in Communication System from RV College of Engineering, Bangalore, securing gold medal in 2009, and B from Adi-Chunchanagiri Institute of Technology, Chikmagalur in 2005. She is presently working as assistant professor in Department of Electronics and Telecommunication Engineering, MS Ramaya Institute of Technology, Bangalore. Dr. Swetha Amit's research work is on the antenna design, wearable and textile antennas, star analysis and reduction in human body, liquid antennas, metamaterials, fractals, frequency selection structures for optimizing the antenna performance, and so on. She has over 35 publications in journals, conferences, patents, book chapters, in addition to her several guest lectures. She also has two ongoing funded projects from AICTE Morrow Scheme and DSP Processing Level 2 for her work on designing the wearable antennas for IoT dynamic connectivity, and Center for Learning for Antenna and Microwave for an amount of around 50 lakhs. She has various consultancy projects as well in designing the antennas, RF microstrip filters. She also has a YouTube channel in her own name, Antennas Enclave, which is focused on discussing the antenna design and optimization in simple ways. She has won Best Paper Award, Association Awards in several conferences for many of her papers related to fractal antennas. So I will now request Dr. Swetha to please take over the session.
Thanks a lot, Yadav sir. Thank you so much. Good afternoon, everyone. I presume the gathering includes students, faculty, and everyone. So I will start with very basics of what antenna is, and then we will go into what all parameters are required if I really want to practically design an antenna. And then we will touch into microstrip antennas. What are the challenges there? How do I choose a particular substrate? What frequency should I choose? What all other parameters are involved for me to design an antenna? Okay, that's the flow of this. That will be the flow of this session. So yeah, so that's what I told right just now. Well, coming to the basics of what is an antenna. So we all know the definition. IEEE has given a very good definition also. So all we have to remember is 3 R's. Okay, antenna is a structure which basically radiates and receives radio waves. So this is all, though it is just 3 R's, if you say, there's a huge meaning in it, right? So there's a structure which completely radiates into wireless, that is unguided medium, and receives back and puts into the guided medium. What kind of waves? It's these radio waves which you are talking about. So I need to know the behavior of this structure, this guy who's there between the guided medium and the unguided medium, to exactly understand how it is doing. Okay. Before we even talk about whether antenna is a passive device or an active device, so we would already know what it is. How exactly antenna came into picture? What made antenna evolve? So the simple example, if I have to give you, so it's like antenna is a structure which is between my wired medium and the wireless. Yeah, we all know that. So why did this come? All I needed to do was throw the energy in the guided medium into free space. Yeah. So if I had to do that, why I needed another structure called antenna? All I needed to do is, if I need to go out of the house, I need to open the door and just leave. So that's what should have happened in wired to wireless scenario, right? So energy or a signal which is in a wired medium needs to be thrown out in the wireless. So there were a lot of disadvantage in wired medium, the distance covered and all those things. Hence, it was thought that let's go into wireless medium. So all we had to do was throw this energy which is in wired into wireless. Yeah. All I had to do was what? A simple example of me going outside. I need to go out. What I need to do is open the door. So likewise, which means if I consider the circuit, what am I doing? I'm open circuiting the ends. Yeah. So if the energy from a guided medium or a wired medium needs to get out to the wireless medium, what should I do? We need to open circuit the ends. Yeah. So, okay. So when we do that, what exactly is happening with respect to impedance? So when I open circuit the ends, assuming that energy scenario, so what happens to the impedance there? In an open circuit, it's infinite impedance, right? Well, I mean, this sounds a bit weird for me. This is the first time in any session I would probably be telling, let's not keep the session interactive. I mean, I cannot do that. We will have a discussion at the end. So since I'm posing these questions, you need to answer to yourself. Okay. So open circuit means impedance is infinite. Yeah. So we have understood so far. So what does maximum power transfer theorem basically tell us? So it says most of the energy from source to the end can travel when the impedance between these two guys are perfectly matched. Yeah, we know that also. So now what is the impedance at the open circuit? It's infinite. Does that mean at the input should I keep infinite impedance at the source? Well, not at all possible, right? If it is infinite impedance, there's no current, no information, no signal getting transferred. Okay. So which means what? There is completely mismatch between the impedance. What happens to the current who is coming from source end till the load end? So he comes here till the load end. He sees that it's an open circuit. So what does the current do now? It has to turn and go back towards the source. Yeah. So that's what happens here also. So this current which is coming from source till the load end is now turning back and going towards the source. So when this is happening, okay, so everything is turning back and going. So what's different to wireless medium also then? Yeah. So a simple example which I always use when I'm teaching the basics of antenna is assume you're walking with a bucket of water. A simple imagination. So you are told abruptly to turn and come back. Okay, when you're told to, when you're carrying a full bucket of water and you're told to turn and come, by any chance would you spill the water? Obviously, yes, right? And then what happens to your speed? Unless you push yourself, the speed can be maintained. But in a normal scenario, if I don't give any extra push, so when I'm turning back, the speed reduces, right? Yeah. So same thing happens with this current who is traveling. He's turning from source, going towards the load end. Since it's an high impedance or infinite impedance, it's turning back. So when it is turning back, exactly same as me carrying the bucket and turning back, two things are happening. Water is getting leaked, and when I'm talking in circuit point of view, current is getting leaked, and at the same time, one more thing is happening: the velocity or acceleration of the current, which is turning and coming back, is changing. So this deaccelerated current is giving rise to charge or something. We know the basics also, right? So in a very simple way, what I can tell is, so when this current is turning back and going, what happens is there is a small leakage current. Okay. So this leakage current is nothing but all the radiation which is occurring in nature now. So if I say a structure is open circuited, the current is turning back and going, and I'm getting too much, I'm getting this leakage current out of this guided medium in space, wireless medium. So this leakage current is what is called as radiation. So how it happens, we will see that eventually when we go into the next slides. So we understood leakage current is the main person or main entity which is helping me in radiation. How much is this leakage current? So again, very easy to remember, as there are 3 R's, you need to know that there are 3 zeros, which means 0.0001% of the current which is getting leaked is my radiation. Okay. So many other things comes when I say about this leakage current also. How much is the leakage current, and how much the leakage current happening? How should I control it? How should I reduce it so that it does not affect human body? Those things we will see in this session and then the next sessions also. Okay. So far, wherever I told you, antenna didn't come into picture at all, right? Did I ever talk about antenna is a structure who is throwing out the energy? No, it's just an open circuit who is throwing the energy out. So let's see, why do I, Why do I need an antenna? Okay. So when we see this, you see the transmission line. Transmission line is the one which is carrying my signal in the guided medium. Okay. So when I'm throwing this out, so assume till the tapered end, so till the parallel ends, the current is turning back and going. So assume I taper it a bit, I extend it. So what happens when I extend? The time taken for the current to turn back and go would be more. Yeah. So more the time for the current to turn back and go, more will be the leakage current. And hence what happens? More will be the radiation. So how much will I taper? I taper, I have parallel plates as such, which is a transmission line. I keep tapering it till both the lines are perpendicular to each other. Okay. So when I taper to that extent, I get the positive and the negative here. So that's when toggle happens, one set of radiation pops out. Again, the next toggle between the positive and negative of radiation goes up. Okay. So this kind of antenna is called what? Exactly the transmission line and the other structure which is there in between these two. So that part of the structure or the extended part of a transmission line or something which is in between the guided and unguided medium, which helps me in maximizing the radiation, is called as an antenna. Okay, that's why we needed the antenna, and few more other things why I need this structure extra. So for antenna, to increase the radiation, increase the current for it to turn and go, increase the leakage current, and hence increase the radiation. That's why we need this structure. Okay, so this structure is now needed for me to transmit between guided and unguided media. How about the other way? Would there be an energy outside and it needs to take? Can an antenna do that also? Definitely yes, it would do that. So how do you know? How do we know that when I have designed an antenna, this particular antenna has to pick that particular frequency which is there in air? How does an antenna know now? Throwing out energy, calling it a transmitting antenna is easy. So from a guided, I have a structure and it goes out in free space. Okay. So before we go on to antenna being treated as a receiving antenna, one more thing which you need to do is, the first thing whenever anyone says design this kind of antenna, the first question which you should know is, what is the frequency of operation? Decide the size of the antenna, because the size of the antenna depends on the wavelength. Okay, the wavelength, again, in order to know the wavelength for designing the structure of the antenna, I need to know the frequency. Yeah. So first question is, I need to understand the frequency. So I will note down what is the frequency. So as we see the Wi-Fi modems in our home, right? So that operates at 2.4 gigahertz, and now it's happening at sub 6 gigahertz also. So if I assume it as 2.4 gigahertz, so I calculate lambda. So these monopole antenna. So it's basically something like, assume I have a wire, a conducting wire. If I give the input at the end, it would give me a monopole antenna. Okay. What happens if I give the input at the in center? Okay. Exactly where I give at the center, it gives me dipole antenna. Yeah. So the same wire which I give at the edges, any one of the edges gives me a monopole antenna. There's a single pole, right? If I do the same thing, if I give the power in center, it gives me dipole antenna. So this is what is the antenna which we just spoke in our slide, which means the transmission line is now tapering into two poles. Okay. So this gives me a complete omnidirectional or isotropic antenna. I will come on to what exactly is a pattern later. So yeah, so when it is a monopole antenna, it would be lambda by 4. Depending on its wavelengths, it will be lambda by 4, quarter wavelength. If it's a dipole, so dipole is double the monopole, right? So it will be half a wavelength. So it will be lambda by 2. Okay. So this is a simple way to design. If I am designing a dipole antenna, I know it should be lambda by 2. If it's a monopole antenna, it's lambda by 4. So all I need to know in the prior is what's the frequency of operation. Cool. So let's come back to antenna operating as a receiver now. So some energy is there. So when I say energy is there, all kind of frequencies are there. I listen to radio, I communicate with Wi-Fi, I have GSM, a Bluetooth, 3G, 4G, all are definitely not operating at the same frequency, right? So there are different frequency. Well, assume I have FM radio right now with me, which is receiving the signal which is someone has thrown out there. So if my FM radio needs to receive that particular signal, how would it know? All kind of signals are falling on it. It's not exclusive that only FM signal is falling on it, right? How would this antenna know? I need that it needs to absorb that particular signal, maybe 100 megahertz signal or something. How would it know? Yeah. So what's the catch in this? Okay. So one more thing, what I need to tell is if I design any kind of RF devices, is impedance matching important to us or not? What do you think? So please answer to yourself. It's very, very important, right? I have a number of components there. I'll have amplifiers, I'll have local oscillators, mix, whatever circuits I have, I should make sure the impedance is matched, because the maximum power transfer theorem says that if I need to transmit my signal from one to other, the impedance should have matched. So does this apply to antenna also? It should apply, right? So antenna also should be designed in such a way that the impedance is exactly matched to the circuit. So how much is this impedance? So universally it's followed that let's impedance. When I'm designing the antenna, let's keep the impedance at 50 ohms. So we know it when I'm designing a circuit, when I'm designing an antenna, always make sure that the impedance goes to 50 ohms, resistive, pure resistive. Okay, when I do this, some magic happens. So what is that is, first thing, what do? When I design the shape of the antenna exactly to its wavelength, okay, so which means I have a FM helical antenna wherein I am receiving my FM signal. It's the simple helical antenna which I would have in my radio. So if the shape of a size of it is designed exactly to tap the megahertz, whatever, lambda by 4, whatever is the size, the shape size of it, it will be very sensitive to that particular signal, which means at that particular signal, for that frequency for which it is designed, its impedance gets automatically matched to 50 ohms. See, as of now, I'm not saying everyone here, most of you would have put your hands in designing an antenna, either in a software tool, whatever. The first thing what you're going to check is how much is the impedance matching. Yes. So which means what, when I design my antenna at that particular frequency, the impedance automatically gets matched to 50 ohms. Huge wonderful antenna. I mean, these are very few things in antenna which made me very fascinated to have a passion for the subject also. See, you're not doing anything to match the impedance. All you're doing is what? Make sure the size of it is exactly reciprocating to its wavelength. When I do that, automatically the impedance gets matched. So now let's go back to this FM radio, wherein all kind of frequencies are falling on it, but it is sensitive to 100 megahertz only, because it is designed, the shape, the size of it is exactly in terms of lambda for that particular frequency. Every other signal for it is falling, the impedance is not 50 ohms. Okay, since though it is falling here, it's not 50 ohms. Maybe any other impedance, reactance would have been added. Hence, it is not much sensitive to it. Okay, so it's as good as telling impedance matching. Okay, why are two people best friends? So you keep telling in your we keep telling in our simple language, frequency matched, impedance matched, all those things. So doesn't that same thing apply here also? So basically, the size of this antenna is exactly proportional to the wavelength of that particular frequency. Hence, it is very sensitive to that. Rest all frequency which is even falling onto it, it's not much interested or sensitive enough to take that signal to it. Okay, so this is how a simple antenna works. So the second thing what you need to the second thing what you would need to know is, first thing, when you design an antenna, you need to know what is the frequency of operation. The second thing you need to ask is, what should be the radiation? How should it be omnidirectional? Whatever I'm talking, going in all direction, or should it be directional? Okay. So as you see the slide here, omnidirectional is something, the dipole antenna. So when I say I'm giving power here, it is in a dipole. So this will be radiating energy in all direction. Okay. So it's called omnidirectional antenna. Or few applications like your satellite communication, which needs to interact only with the earth station. So then I would probably need a directional antenna. So this is a second criteria which I would need to know when I'm designing a antenna. So here when we see, so isotropic is an ideal one, like which is told that when an antenna pops out energy, it is isotropic. It's radiating in all directions. The very closest antenna which gives almost an isotropic, but I can't call it isotropic. Practical scenario, we call it as omnidirectional antenna. Okay. So this omnidirectional antenna, as you can see, is the dipole antenna, which we just spoke. The transmission line, which gets tapered to perpendicular, is the one example of dipole antenna, which is throwing out energy in all directions. So basically, it's not all direction. You get a donut shape, or you call it in figure of 8 or whatever. Yeah. So hence, practical antenna, we don't call it as isotropic because there are few nulls when we talk about the almost antenna which gives out in omnidirectional, which is dipole antenna. So hence, practically when I talk, either it is omnidirectional, or do I need to put a directional? Okay. So as of now, we know only about dipole antenna, right? Which is putting out energy in all directions. So the same antenna, if I want to make directional, what do I do? Now this energy, this antenna is putting out in all direction. So I don't want it to happen. I want it to go in one direction. So as good as telling right now what I'm talking is going in all direction, right? What if I stand against the wall? Yeah. So when I stand against the wall, obviously my voice is not going, it's just from 0 to 180 degree. Okay. So what should I do to the antenna also? Put a reflector behind it. So for the same dipole antenna, if I put a reflector, so the energy which is going back also gets reflected and comes to front. Okay. And but then again, I want it only in one particular direction, not 0 to 180 degree. What do? Can I keep a lens? So if I want my voice to be focused, so usually what you do is you put some directors, you put some lens, so that the energy which is there just completely gets converged into one direction. Okay. So this arrangement of a dipole antenna, wherein I put a reflector at the back and some directors at the front, is called as Yagi-Uda antenna. Okay. Amazing one. So which easily gives me a directional antenna. So okay, that's the concept of directional antenna. Now what I do, since whatever I'm talking right now is something called as how much is the distance covered. Right now whatever I'm talking, maybe it's covering 10 meters or something. What if antenna is also talking at some pitch with some power given to it, is covering around 10 meters. So I need to increase the range. What do I do? Me sitting here, I want it to travel, so I shout. Yeah, I raise my voice. Can I do the same thing with antenna? So question is, if I want to increase the distance of coverage, can I give more power to it? Will the distance increase? Obviously, yes. As good as what I'm talking, if I increase my pitch, the distance will cover. But can you play with power? Can you play with increasing power? Definitely no, right? I mean, we are surrounded with many living things here. It should not affect them. So there's FCC, Federal Communication Commission, which has given us a range of power beyond which we cannot go. So now the question is, I cannot play with power. What will I do so that it increases the distance? So for that, we have a lot of other things, go to arrays and whatever. So right now what we have done, converting this dipole antenna to a Yagi-Uda antenna, don't you think the distance would have increased? Right now what I'm talking, I make sure I confine it and throw it in one direction. The distance would definitely have increased, right? Yeah? So whenever we are designing an antenna, omnidirectional is taken as ideal case. The directivity is taken as 1. Okay. Any other antenna which you are designing, so directional, whatever, will be more than 1. The reason being, as I just told you. So next question what comes is, if I tell you to design a directional antenna, you should know how much should be the directivity or how much should be the gain. That's the third question you should be asking when you are told to design a directional antenna. Okay, if it's omnidirectional, I know its directivity is less. We still can increase it by making some arrays and all those things. But with directional, we need to check this. Okay, what other things do I need to bother? We just saw that the first thing I need to remember is what is the frequency. I need to know what kind of radiation pattern it is. And the third thing is I need to know what is the gain or the directivity or how much. This easily tells me how much, what is the distance covered. There's a relation equation which I'll be discussing in the next slides, which tells me if I know the gain, I will easily know how much is the distance covered and everything. Next thing what comes in the picture is what should be the polarization. Okay, so polarization, we have 3 types. That is linear polarization. Either the electric fields are going in vertical direction or they are going in horizontal direction. A simple kind of polarization. If you are not given any specific thing about polarization, you default take it as linear polarization. Next comes is circular polarization. So it means the signal, the explanation is here, the animation you can see here. Circular polarization, either it would turn as a right hand circular polarized or it would turn as a left hand circular polarized. You turn your fingers, you will know it. Elliptical is the best one because the major axis and the minor axis are not the same. So there will be a small delay there. So which means I have more control over the signals which are going between the major axis and the minor axis. As simple to keep it as of now. So this application is used in right now in DD. So basically, initially what happened was, so assume I have 2 adjacent signals, which is traveling, which is coming from a satellite. There are many chances that it may get interfered, due to a lot of reasons. So assume both are in linear polarized. So if both are horizontal polarized, both are vertical polarized, both might interfere, right? Obviously. So what if I make these adjacent channels? Okay, at my home, most of the time it's these Cartoon Network or the Pogo going on. Let's take that as an example. So assume these 2 channels are adjacent to each other. So both are linear polarized. Okay, so by the time it's coming from there to my home, long distance traveling, so it may happen that they interfere with each other. So what's the best thing to do? Make one channel right hand circular polarized, the other one left hand circular polarized. Okay, so then both they don't know each other behavior. So that application probably happens. You need to check about the circular polarized or elliptical polarized when it comes to the communication. So if it is not told, you just stick on to linear polarization. Okay. So that's about the external. In the unguided medium, this is what I need to take care. So what about in the, so this antenna is a structure now. So what should I take care of? So just now I told you that between the source, which is throwing out energy, the impedance will be 50 ohms. The transmission line will also have an impedance of 50 ohms. How about the antenna here? Should it also have an impedance of 50 ohms? Definitely yes. So all these impedance should be perfectly matched. Else what happens? I just told you current will turn back and go. This is in our RF or transmission line language. It's called reflections. Yeah. So S parameters is the one which basically talks about how much is incident and how much is reflected. Okay. So what happens is, so the current is coming till here, all the voltage, whatever we are talking about, turns and goes back. Velocity has reduced. Okay. The wave is coming and one more wave. If there is a mismatch, now turns back and goes. So how much will it turn back and go? If it is completely mismatched, so as in our case wherein we opened the door for energy to go, no, it is infinite impedance here. So there will be total internal reflection. Okay, so assume I have designed an antenna. I am not very sure whether it is 50 ohms or not. So we do check in HFS, I mean, whatever simulation tool we are using, you may get exactly 50 ohms. When I fabricate, when I attach SMA connector and everything, there might be some fabrication losses, and I may exactly not get it at 50 ohms. So there is some reflection, small part of reflection. So when this reflection is coming, the speed of it will be less than the one which is going, right? So in such case, what happens, at some part it will be constructive. Both looks like it's added up. At some part it gets, you feel like it's cancelled out. So when someone is seeing from top, or someone doesn't know that these things are happening, for him, it feels like the waves are just standing there at exactly that point where both are cancelling. No, one is at the major, one is at the minor damped. So if I exactly put my probe at that point and check, what happens is, I'll feel like there's no energy at all, but that's not the scene, right? It's not happening. Hence, these are called as the standing waves. So they're just standing there due to these reflections which is coming. So it's not standing everywhere, right? It is more, somewhere it is less. So I need to know what is the maximum, what is the minimum. So this is called as standing wave ratio. And I always measure this in terms of voltage. That's what we see on the slide. It's voltage standing wave ratio. Okay, so that's these three parameters which are there in the starting: VSWR, S parameters, and impedance matching. If my impedance matching is perfectly at 50 ohms, my VSWR will be 1, because Vmax and Vmin. See, something is going, nothing. If nothing is coming back, if the antenna is perfectly matched at 50 ohms, nothing comes back, right? Everything gets absorbed here and it's out in free space. So in this, what happens? There are no reflections, hence Vmax or VSWR will be 1. So when VSWR is 1, S parameters, when we talk about incident to reflected, all those things, so it will be infinite. So that's how we can easily compute that it's S parameters and how exactly is the impedance matching happening or not. Okay, and then is power constraint. Obviously, I need to think about it because SAR comes in a picture. So that's a very, very important thing which I would be talking about in the Wednesday session about specific absorption rate, how much power can enter you so that you don't roast, something like that. So we'll see how much is the minimum power which, or the maximum power which is given by the Federal Communication Commission, which I can easily take and nothing happens to me. And near field and far field. So I have an interesting slide next. I will talk about near field and far field there. And then comes, so far whatever I have told, I have only spoken that if you want to design an antenna, all you need to know is frequency. And then frequency, the size you would know, lambda, in terms of wavelength. Yeah. Did I ever speak that shape is fixed? No, right? If the shape was fixed, probably the antenna research would have stopped. I mean, shape is something which is completely in your control. Depends on different application. You can, I mean, few are standard that you cannot touch. But when you come to microstrip antenna, I mean, you name it, the shape comes. As long as it meets your specifications of radiation, pattern, the gain, whatever, any shape is done. Hence, probably antenna research is getting more fascinated. Meta materials are there. I mean, you guys should check what are fractals. I mean, nature, whatever shapes are occurring. So that is taken into designing the antenna also. How cool is it? Okay, so we need to know whether do I need an aperture antenna? It's just a wire antenna, or should it be a microstrip antenna? So it depends on your application. You need to know, decide on these things. So if it is something which goes inside your phone, it will be a microstrip antenna. So aperture, wherein you need, it's like your horn and antenna or something. So that depends on your application. Okay. Next comes is, am I communicating at one frequency, or I need to design an antenna which covers many frequencies? Okay. Example, let's talk about the mobile itself. Earlier days, we had the cell phones, the first originated cell phone, which had only GSM or probably SMS also. Yeah. When I say GSM, it's just one particular frequency. So what kind of antenna would I use among these three, what I have listed here? It would be a resonant antenna. Since it is working at one frequency is called resonant antenna. That frequency with which it is operating is called resonant frequency. Yeah. So next what happened? So many things came into picture. One antenna is doing so much work now. So many different communication are happening at different frequencies. So what does that mean? Can I have n number of antennas in my phone? Not possible, right? So what happened after that was, let's design an antenna which covers a very wide band. That's possible. Those are called as ultra wideband antennas. Okay. So what is an ultra wideband? Wideband, you know, the antenna which is covering a higher bandwidth. Ultra wideband is a word given when an antenna covers a frequency bandwidth of more than 500 megahertz. Okay, anywhere, no matter what is the RF frequency, if it covers 500 megahertz, it's called as an ultra wideband antenna. Okay, so assuming my phone has these applications which is working at GSM 800 900 megahertz, 2.4 gigahertz, FM and all those things, so they designed the ultra wideband antenna then. Okay, so it's an ultra wideband antenna. Good enough, right? One antenna is now catching all the frequencies. Yeah, but is it good? Is it good to have an ultra wideband antenna in my cell phone? So now what's happening? Am I using all the frequency in the wideband? In the wideband which is covering? Definitely no, right? So I have only particular set of frequencies which it needs to touch. So why will I waste the rest of the energy in the wideband? So then what came up was this multi-resonant option. Okay, so we need to design an antenna which gives multi-resonant application. So now the point is, if I need to design an application, an antenna, which single antenna need to work for a number of frequencies, you can design a multi-resonant antenna. Nowadays, that's what is happening, right? We know that 2.4 gigahertz Wi-Fi is completely getting crowded. The next frequency band, which is touching, its 5.8 gigahertz. So a single antenna, if it can balance dual bands, it is good enough. So that is possible. Then again, depending on the shape of it, how do I put the slots? How do I make the structure so that it gives me a number of bands? So all those things are very tricky with a microstrip antenna. Okay. So we have always spoken about good things of antenna, right? Let's see what happens if I do something and what is the compromise or trade-off do I need to do. Now, if I say ultra wideband antenna, I'll be designing. So few applications need ultra wideband antenna, wherein I am if it is operating at single frequency or I need to push in a huge data. So we definitely need to design an ultra wideband antenna there. Okay, so if it is an ultra wideband antenna, so it's as good as telling the energy is now completely distributed over the band, the gain reduces. Okay, as good as me talking, it's circulating in all direction, or me speaking in one single line and the directivity is more. Same thing happens here also. More the bandwidth, higher the bandwidth, the gain of the system reduces. So you trade off there. You cannot make sure I have a huge bandwidth and gain is compromised. So you need to design, shape the antennas on a microstrip so that you take care of these things. Okay. Then again, acceptable lobes. So practically, when I say directional antenna, it's like throwing energy in only one direction. Does that happen? Ideally, sorry. Does that happen practically? No, right. We get a lot of side lobes. We get a lot of back lobes. How well should I manage these adjacent lobes and the minor lobes basically, so that most of my energy is not killed by this adjacent lobes itself. So I do need my energy to be constrained or to be confined in the major lobe itself, right? So that side lobe reduction itself is a huge research happening with respect to this RF and all. So this is one very important formula you would know about it also. It's the Friis transmission formula, which speaks about if I have a transmitting antenna and a receiving antenna, both has its own gain. So I can easily make out with what power. If I say I'm transmitting at some power, I know the distance, I know the gain of me transmitting, the other antenna who is receiving there. We can easily calculate with what power is he receiving if I know the distance and everything. So this is one very powerful formula which we need to know when we are designing many things. Maybe I know everything, I need to calculate the gain of the other person. Even if it is unknown, we can do it. So coming to near field and far field, few phones have this NFC symbol, like this Harry Potter lightning. I'm sorry. Behind your phone, you have this lightning symbol coming up. Okay, so that's the NFC, but I have not seen many using it also. What's the reason? Okay, so please watch this video. Okay, I am not sure why I'm not able to play it. Let me.
Okay, just try play video when sharing the screen.
Okay, I have not shared the screen. I have shared the PowerPoint. Maybe that's the reason, no?
Yeah.
Okay, I will just give me a moment. I'll stop sharing it and reshare the complete slide. Okay, not happening yet.
Try to check the share video while sharing. Share file.
Yeah, I have done that.
Yeah.
Can you see the screen?
Yeah, screen is visible.
This is the max.
Play, click on the play.
Yeah. Okay, this is the point wherein assume that I have thrown a stone in the water. So right at that moment when the stone is hitting the water, the disturbance, right? We all can imagine it. And then what happens? The ripple starts occurring. Yeah. So this easily we can relate it to the near field and far field concept. So basically what it is wherever the disturbance is occurring is my near field, and wherever the ripples are occurring, we can consider that as a far field. Okay, so what does this tell us is when antenna is throwing out energy, the moment it's throwing out, exactly at that neighboring point, the electric field and magnetic field are not perpendicular to each other. Okay, whenever we say radiation has happened, it's no more about voltage and current, which we talk in guided medium, right? It's about the electric field and the magnetic field there. Okay, most of the boundary condition of whatever we talk, we assume that E and H are perpendicular. This rule, what does it say? If assume this is my direction of propagation, electric field is perpendicular to this and the magnetic field, all three are perpendicular to each other. So when this is taken into consideration, our concept or our analysis gets very easier. So exactly where this antenna is throwing out energy, there's this disturbance. Okay, so that's what we call it as the Fresnel region. So which we can calculate it using the equation also. So which means exactly where the disturbance is, E and H are not perpendicular. Hence, I'm not, though near field is not that a boom now. Not much research has happened with NFC. But if it happens in a very nice way, NFC can be used for very, very, very many applications. So after that, when the ripples start occurring uniformly, right? After I throw the stone, the disturbance occurs and then the ripple occurs. So this is what gives me the far field, okay? Reactive or Fraunhofer region, what we do. So every time when you design an antenna, you have designed two antennas, assume one for a transmitter and one for a receiver. You should know how near or how far should I keep it. For that, you need to calculate 2D square by lambda. You would have done in your labs. So the reason being, if I keep them too close to each other, then the E and H are not perpendicular. For me, understanding that is very difficult. So hence I keep them quite far so that it understands this constraint. The distance between these two should be more than 2D square by lambda. D being the dimension of the antenna. Like if it is a monopole, lambda by 4, if it's a dipole, it's lambda by 2. So when I calculate that, I will easily get the distance there. So this is about the near field and far field. Coming on to, so now we have basically understood basics of antenna, no? So what are the parameters do I need to know if I need to fix the frequency? I mean, fix the frequency, know the radiation pattern, directivity, gain and all. So size to some extent I know now. How about the shapes? You see here, I mean, each one has a different shape. What made me design that, or what made us design that? Let's go into step by step. So as the word says, it's definitely an antenna. What's a microstrip antenna? Strip is what? So we know it's a small thing which just sticks onto something. Micro, it's very, very small. Hence the name microstrip antenna. Okay. So this is how it looks like. So I have, okay, in a very simple thing, if I want to tell antenna whatever, or this strip whatever I'm taking should be a conducting material. Yes, else how will it even radiate, or how will it act as an antenna? It should be a conducting material. Okay, cool. So I am putting this strip onto something. So holding this strip, right? So who is this someone? What material should be this? So can it be good conductor? No, then I cannot differentiate these two guys, right? So should it be a bad conductor? Definitely no, current will not at all travel there. So what should it be? So what the material what I choose here is called as a dielectric material, okay? A substrate, okay, which is having some dielectric constant. So its conductivity is in between these two. So in a simple way, what we can tell is we are choosing a semiconductor material, something like that. It's a dielectric material. So now I put a strip onto a good conductor strip onto a dielectric material, okay? And then what? That's it. If I give power to that antenna, will it radiate? So now what should happen when I give the power to antenna? Anything what you do, you build a circuit, everything is grounded, right? So whatever fields are emerging due to this giving power to this antenna is now should reach below the substrate. On top of it is my antenna, and below is again should be someone else. So this is a ground plane, again a good conductor. Okay, so on top and the bottom are my good conductor, and in between is my dielectric material. Okay, so this is a simple way how we can look into a microstrip antenna also. And there's okay, so if I look into strip lines, so this is how the radiation happens. So when I feed the antenna which is on top of it, all the energy will now reach the ground. Are we seeing the same? No, right? The green line also says that some of the energy is going into air also. So due to this, what happens, we will see. Microstrip is one case. There's one more case called as strip lines. Okay, so strip line is something wherein I have a substrate, assume okay, so I'm sitting in my daughter's room, hence so all I can see is find as a toy. So assume this whole thing is a substrate. Okay, what if I put this strip, which is a good conductor, in between these two, this yellow and pink box? If I put it exactly in between, it's very good for me. I mean, on the top and bottom is my ground plane. Yeah. So doing this has a lot of advantage. Now, previously what we saw here is the energy, whatever I give to the antenna, is now reaching the ground, but few of the energy is going into air also. Yeah, which means the transverse electromagnetic wave is not pure. Which let me tell again, the dielectric material is chosen, which will have a dielectric constant epsilon r of whatever number it is. So that also has a huge impact. What number should you choose to design an antenna? We'll see that later. But this epsilon r matters to me. So since now the radiation is entering into air also, epsilon r in air is 1. So there are two things involving, two dielectric constants are involving. So it is quasi transverse TEM waves coming from a microstrip line. So, but when I look into a strip line, it is pure TEM waves which is coming out, which is very good for us. Likewise, see, if it's a strip line, as we can see, it's embedded inside the substrate, and on the edges we have the ground plane. But wherein a microstrip antenna, it's on top of it, and the bottom is a ground. But strip line gives me a pure TEM. The microstrip line gives us a quasi TEM. but which is good. Strip line is definitely good, but the fabrication, putting the strip inside the substrate is not that easy. Hence, for a simple research, what we are doing, a microstrip line is easy for us. So coming on to in detail design of a microstrip antenna. This is how, yeah, I already told how it looks like. Now, if I'm sorry, if I'm designing a three-dimensional antenna, what is the thing which I need to know in order to know its size? The frequency. That's all I need to know, right? It's in terms of wavelength. Okay, but when it comes to microstrip, it's just not the frequency which is influenced here. What other things are influenced? Since the antenna is put on the substrate, I need to know the dielectric constant of this material. One more thing I need to know is what is the height of the dielectric material. So we see the H here, right? Yeah. So these three things are very important for me to know. Frequency, I can't do anything. Someone would have given you design an antenna for this frequency, that will not change. But if you have an option to choose which substrate is good, there are a lot of advantage of choosing a substrate which is as low as possible to as high as possible, and also playing with the height. So in market, whichever is available, see, my research basically started with what is available in market. That's our FR4, right? Fire resistant dielectric constant in terms of 4.4 or whatever. So we easily available, we took it, whatever height it was, we took into consideration. But then eventually I understood that the same FR4, you can get it for different height also. So when you play around, you completely understand what is the impact of many other things with respect to wideband, with respect to directivity, what is changing if I have to play with a different H and different epsilon R. We will see that in the next slides. Okay. So these three factors are affecting me to decide the size of the antenna. Okay. So here comes, okay, this is, okay, I'll talk about this and then go into the equation part. So as we see here, so since my microstrip antenna is a quasi TEM1, all the fields which are emerging on the antenna needs to go into the air, needs to go into the ground plane, but it's also going in the air. Hence, when you are calculating the few length dimensions of this antenna, you are not directly taking epsilon R into picture. You are taking something called as epsilon R effective. Yeah, it's as good as, in a very simple way, you have to say, means it's the average of these two, epsilon R in air and epsilon R in, it's not average, there's an equation for it. The reason why you do epsilon R effective is this: since the energies or the electromagnetic waves are not completely confined inside the substrate, it's going into air also, hence I need to take epsilon R effective. Now I give power to antenna, what should it do? Few of the energy is going out, space wave radiation. It has to simply touch the ground, right? That also doesn't happen. Now look at those, something called a surface wave. What's happening? The energy, I mean, you literally cannot hold a stick and beat it until it reach the ground, right? Few of the energy does get escape to the edges. So that is complete waste for me. Surface wave, that occurs. So there are a lot of advantage when I increase the height. Okay, but what happens to the surface waves? Surface wave will also increase if I increase the height, right? So there's a lot of trade-off between those two balancing. Okay, this diagram explains me how exactly that happens. Yeah, this I told you, before you design an antenna, I need to know what is the frequency, dielectric constant, and height of the substrate. This equation, we get it everywhere. If I want to design a simple patch, is a rectangular shape, okay? The length and width of it can be calculated with these equations. So then again, when I see here, it's the width, the first equation, got it. Epsilon effective is calculated because the radiation is going in air and in the material also. And what is this third one? Delta L, very important thing, very tiny thing, but very important thing. So it so happens that, okay, let me go back to this diagram. Yeah. So there's this dimension of this antenna. This is W, assume some dimension L or W. So since these energies are mostly confined to these edges here, okay, and it is reaching the ground, you feel like there's a small extra size of the antenna which has come up, which you have extra size increase. Okay, so what you do before you design, you make sure you delete twice of this delta L. Okay, it happens. Microstrip has that. You call it as a very nice feature of a microstrip that happens since all the energy is confined to the edges and it is reaching the ground. So hence what we do is we always, when we are calculating, we remove this. Else what will happen? If you don't remove this, now you have calculated L and that is given extra. Now my resonant frequency will change because the dimension is not exactly to that frequency what I have designed. So I need to remove here, and there it will be compensated by my electric field, the fields which are emerging. So that we have to do. And next is, depending upon, once I calculate the patch length and width, now I need to know what should be the size of the substrate also. So very easy way is leave 3H all sides. So this is how for you start. Then probably a lot of optimization things are involved, but for a start, this is very good. Okay, and how do I feed this antenna? So assuming this, okay, let's take this white thing is the antenna, is the substrate, and this whatever structure you see is the antenna there. Okay, the strip which we have pasted. So how do I trigger this? This is exactly in between, right? This is at the center. So how will I trigger this antenna? So I can draw another strip line here and give it at the edge. That's very good thing. Okay, I will be discussing feeding technique also. In this equation slide, what it says is, if I am taking a strip line to the edge and giving a power here, as good as I have a strip line, this is my hand, this is a substrate, antenna is exactly in between it. If I want to feed it, a very simple way to start with is extend the line and give it the corner of it. So the width of it matters to me a lot. I just can't have, the length is fixed. It's 3H all sides. The width of it matters to me a lot. So you can easily calculate with this expression. Why is width important is, see, when you are feeding from a SMA connector or whatever power is coming, it's 50 ohms, right? I should make sure the same impedance is touching the antenna also. Okay, I would have designed it, but the strip width, this small strip which I use between the SMA connector and the patch, should also be at 50 ohms. Okay, so width decides it. It's as good as, okay, consider two pipes, which one is ½ inch and one more is 1 inch. In which of it is the water flow more? Sorry, I'm giving very silly examples, but okay, I think you can understand it better. So two pipes, in which of them would the water flow be more? In 1 inch pipe, obviously the width is more. What, same thing, let's talk in terms of current. In which of these will the current flow be more? Assuming in the bigger one, yeah. When the current is more, how about the resistance offered by it? In 1 inch pipe, the current flow is more, hence resistance offered is less. In the smaller pipe, current flow is less, the resistance offered is high. Okay, I can come in between these two and make sure the width is so much that how much ever current it is giving, the resistance offered is exactly 50 ohms. Can I do that? Yes, it is possible. So, okay, this expression exactly gives me what should be the width of the 50 ohm line. Hence, I am not playing around anything now. Okay, so easily I take the strip outside, give the power at the end. Possible. So this is one simple example which I've done, which I've calculated for at 2.4 gigahertz. So these three things I need to know very well: the thickness of it, dielectric constant. So this would be the dimensions of it, of an antenna. So I will share the presentation. You can recalculate. You can play around different dimensions. So that's what is a nice thing. Play around different thickness, play around different dielectric constant, simulate it, find out what is happening here. You will be very, very interested to know. I mean, you can easily understand antenna when you play around it, and especially with these tools, so many things to understand. So I mean, when I say electric field and magnetic field are there in air, imagining this three-dimensional is not that easy. When you have these tools wherein you can easily visualize them, how is the current distribution happening, how exactly is the electric field and magnetic field popping out of the antenna, it makes life a lot easier to understand. So from where did that delta L, if I want to calculate, I can also use this formula. It's same as what I told previously. or somehow the delta L equation is very big. I'm too lazy to calculate. So what you can do is, I can easily know the height of the dielectric material, and delta H will approximately be 0.5 H. I just played around. This is given by the, I mean, if I want to concentrate on a dominant mode being operating there. Yeah, so as we see the first diagram there, here what is happening is you are feeding the microstrip line from the edge, or it could be a coaxial feeding. When you look into this coaxial feeding properly, the port is not exactly at the center, right? I mean, you see a dot there where exactly the power is given below this. So antenna is here, this is the substrate, and this is my antenna. So I have to give power to it. So what I can do is simply drill a hole and give power to it through SMA connector. Easily possible. It's possible. It's easy also. But what is the main catch? Why am I going to the edge feeding when coaxial feeding is easy for me? Reason is, okay, simple way. When the current is given to this antenna, at the center the current will be maximum, and as it goes to the end, the current becomes zero. Okay, you remember like this. So at the point where at the center, since current is maximum, what happens to impedance? Zero. Okay, and as you go, current is maximum. Okay, what did I tell? Oh, sorry. In center, the current is maximum, so there is no resistance offered to it, correct? So as I go toward the edges, the resistance changes. Okay, in between these two, center and the edge, can I, while going along, can I hit a point which is 50 ohms? I do encounter a 50 ohm line, right? So in coaxial feeding, I need to tap that 50 ohm point. So there are quite some equations to calculate how much it is and all. Even though you find out that point, no, you drill a hole, you place the SMA connector, fabrication should be perfect. Else you would have a lot of losses there. Hence, more or less, we somehow compromise with the microstrip line itself. So we spoke about a simple rectangular patch. There can be any shape. I told you, no, the size is fixed, but the shape you can always play around. Depends on whatever it is. If a simple hint, what I can give you is, if you are designing a resonant antenna, go for a rectangular shape. If you need a wide band, okay, go for a circular one. So the variable antenna which I have designed, assuming that I have used it for health monitoring applications or whatever. So a lot of data needs to be pushed out. So we designed an ultra wideband antenna with a simple circular patch. So as we can see here, the rectangular patch we discussed, for a circular patch, I can easily, the equations are available. I can easily calculate the radius of the antenna, radius of the radiating element. And I will easily get a wideband. So probably you can do is fix a frequency, design both rectangular and circular, look at the behavior with the same material, with the same dielectric constant and height also. So design a rectangular and a circular, we can easily find out what is the difference there. Okay, and advantages are many. Easy to fabricate, feeding is okay once we know a good fabrication. I do get moderate directivity. So let's come into what are the trade-offs and disadvantages. The bandwidth gets lower when I'm using a microstrip than compared to these aerial antennas, three-dimensional one. Okay, large power can't. And if I'm going at, I mean, now people are talking about millimeter wave and all. No, you cannot use a simple FR4 and all. So you need to play with different substrates. You need to understand the behavior at that frequency. Yeah, then again, dielectric losses are evidently there, and also surface losses. Since I cannot control the surface losses. Feeding method, we just discussed, this is one type, the coaxial feeding, wherein I exactly tap my 50 ohm and drill a hole and give it. So that's my coaxial feeding. What I explained previously was edge feeding. So I had my antenna, I took a strip line which is 50 ohm line and gave it the edge. Okay. One more very easy way is, so as I told you, so this current here is maximum, or impedance or resistance is zero. As I go along to some other distance, there will be my 50 ohm point. So exactly at that 50 ohm point, if I tap and cut off that patch area and extend the strip line, which means what? Wherever I have cut off this patch, no, the rectangular patch which I would have cut, and I'm extended till center. So that is exactly my 50 ohm point. So now I can somehow be very happy that I have touched the 50 ohm point and power is touching till there. So easy way, edge feeding or inside feed, it's going inside feed, or if you want, or you have coaxial feeding. There is one more thing, proximity coupled feeding. Here what you can do is, microstrip I cannot compromise, let it be on top. How about I introduce one more strip line in between the substrate and give power through it or something. Then again, if your fabrication and all is very good, you can try this also. Multi-layer fabrication, that's the only disadvantage it has. So a comparison of all kind of feeding techniques are given here. Okay. So what should be the radiation efficiency now? So which means if I take a substrate which is having very thin, which means electromagnetic wave can enter through it very easily, then would my surface wave be decreased or something? So that is something which you can again think of. So there are a number of, anything which has a dielectric material, which is a dielectric material, can be chosen as substrate. So for a researcher or something, you need to play around different substrates to understand the impact of it on many parameters. For example, for example, the directivity. Okay, directivity is more or less not much related to the substrate thickness. Okay, directivity is higher for lower permittivity. Okay, if I take a material which is having a dielectric constant of 2.2 or something, or an RT duroid, a Rogers RT duroid 1, so directivity, I get a very good directivity there. But the patch will be larger because the dimension will increase now. Okay, if you do not have a constraint that the antenna should be very compact or something, go to a material which is having lesser dielectric constant. You get a good directivity there. Okay, so for directivity perspective, it's just the epsilon r I need to bother. The thickness of it is not much of impact on a dielectric on the directivity there. Okay, so next thing is, we are talking so much about directivity, gain and all. This basically is how much is the distance covered. That's all in a simple way. If I want to increase it, okay, so if I want to, if I'm calling out my friend, he doesn't hear to me. So what do? I call another friend, both of us shout, and so that the other person listen to it. Okay, so that's all is happening with arrays also. Two similar antennas. When I say two similar antennas, either it should be dipoles or patch antennas of same shape, same size, and everything. So similar antennas, if I feed them, arrange them in a linear matrix form or whatever, it forms an array. So when I do this, given the same power to it, it covers more distance. It gives me more directivity or gain. Okay. So then again, when I arrange, this is one simple thing which we need to know before we even construct arrays. So what it is I have two elements or n number of elements which are arranged in a linear fashion. If I feed them with same amplitude and same phase, what happens? If I feed them with same amplitude and opposite phase, what's happening? So the radiation pattern changes as we see here. So the first case when I take, if I feed the amplitude antenna, array of antenna with same amplitude and phase, I get a radiation pattern which is perpendicular to the axis of the antenna. Assume this is my axis. Two antennas are placed here, one here and other one here. If I feed them with same amplitude and same phase, I get a radiation pattern which is perpendicular to it. Okay, so the same two antennas which are at some distance to each other, if I feed them one with same amplitudes but with different phase, so assume 180-degree phase shift, then I would get a radiation pattern along the axis of it. And that's something very interesting. There's an example again for this. I'll video. So this, I have taken an example of throwing two stones at the same time. Now what should happen is, see, when I throw one stone, ripples occur, right? What happens when I throw two stones at the same time? So according to this, what happens, in some direction the ripple should cancel, and in some direction the ripple should add up, right? And the same video shows about, let me throw two stones at different timing. So the opposite happens. So thus I get a broadside or an end fire
array of 2 point sources. Point source fed with same amplitude and same phase. The ripples or the radiation along the axis will cancel out, and the ripples perpendicular to the antenna axis adds up. This configuration of point source fed with same amplitude and phase gives us broadside array. The next condition is antenna fed with same amplitude and opposite phase. It's 180 degree out of phase. This cancels the ripples perpendicular direction and adds along antenna axis. The wavefronts get stronger along the axis. This kind of antenna configuration is called end fire antenna.
Okay, so I don't know how much you could understand with this. Probably you can try doing this. Throw two stones completely in a stagnant water and analyze where exactly the ripples are getting cancelled off and where exactly it's adding up. I mean, that's the concept of this end fire and broadside. So this, what it says is, I get a broadside when both are at same phase. Yeah, I get an end fire when both are at opposite phase. So which means the phase is at 0 degree, I'm getting this. When it is 180 degree, I'm getting this. How about I keep changing the angle between 0 and 180 degree? Would I keep changing the, would I get a radiation pattern at different angles? Yes, right? So this will help me in beam steering also, if I exactly know what is the phase with which I need to phase these two antennas. Okay. So that's about array of antennas. And nowadays it's more about conformal antennas, right? The substrate, whatever you choose, let it be as thin as possible. One advantage of substrate height being as thin as possible is the surface loss can be reduced. Okay, and one more thing is I can bend it. Okay, a lot of applications which would involve that the antenna will take the shape of the device on which it is being put on, like, oh, as you see there on the slide. So it wouldn't be that comfortable for me if the antenna is this thick and like a rectangular patch or something. If I can wrap it around conformal antennas, that's something which is happening in today's research and everything. So all these things, it's just not that I keep in mind. You start your journey with what? Knowing the frequency, analyze the antenna, what should be the size of it, what should be the shape of it, depending on directivity, gain, what should be the polarization, should it be wide band, should it be narrow, should it be multi-band? Okay. So once I know all these things, I'll start designing it on paper with equations, diagrams, and everything. Yes, you have a lot of simulation tools available now to prove or to test it before I even fabricate or whatever. So simulation tools like ANSYS has this HFSS, FICO, ADS. There are n number of tools, whichever is convenient for you, whichever is you're handy on, you can use that. So that at least gives hope that whatever I'm designing is in the right direction or not. Then yes, you can fabricate, test it for good impedance matching on a network analyzer, and with the help of an anechoic chamber, you can completely test the radiation pattern of the antenna behavior also, whether it's omnidirectional, directional, what is the gain of it and everything. So this is the last but one slide which talks about what all should I bother when I choose the material, substrate material. The shape, yes, since that is not fixed, you can play with the shape also. You can play with the substrate thickness depending upon what material you choose, and dielectric constant also. What does these things impact on? It will impact on your directivity, gain, the bandwidth, and the polarization also. Okay. If I increase the substrate thickness, okay, so if I increase the substrate thickness, the frequency shifts to a higher side. The directivity, gain, bandwidth, everything increases. So first thing is your H is directly involved in the finding of patching, the height, length or the width. So frequency definitely shifts if the substrate thickness goes high. But the good thing happening is bandwidth will increase, the directivity and gain will also increase. But increasing the thickness means what? This electric field from the antenna should simply come and touch this ground plane, right? So it's not being too obedient when the substrate thickness is high. It goes to the edges. Surface waves are created more. So you need to be a bit careful, trade off. If you're ready to compromise with surface wave a bit, so you can choose a substrate which is having higher thickness. What happens if I choose a dielectric material which is increasing? So here what happens is the main parameters of bandwidth, directivity and all will decrease, but the antenna size rate. So if you are given an application which says a very compact antenna and all those things, you can somehow compromise with the gain or the bandwidth. Probably it would be a resonant antenna or something. So then you can go with the higher dielectric constant materials. So okay, this is about it. Well, in our college, we are working on a project at MS Ramaya Institute of Technology, wherein we have got a funding from VGST, Vision Group of Science and Technology, to set up a microwave and antenna lab. So we are planning to have a center of excellence also for it. So once this is due to this Corona time, it got delayed in getting the material and everything. So once that is done, probably whoever are interested, we can have a collaborative projects. We are planning for internships, many other things. So once it happens, I just thought it is a good platform for us to share about this information. Much more will be put in the website also. So whoever are willing for any collaborative research, we can definitely jointly work and learn together about it. And one more thing, I have a YouTube channel. It's called Antennas Enclave. So yeah, it's just the channel mainly focuses in explaining the concepts as simple as possible. So the same bucket examples or what throwing a stone is what I talk about. I mean, this is all probably even I have remembered it for this long. And it makes me very interesting to even learn more about. See, doesn't it fascinate you when you say all you have to do is design the antenna for that the size, but the impedance matching automatically tunes to it. Then there are many such things which fascinates us a lot with respect to antenna. So whoever is interested can please subscribe to the channel, and we can do a lot of things in a very simple way. Thank you so much. Thank you so much for patiently listening to me. Though you were not given the liberty to interrupt me, I seriously thank you for it. Any questions or something we can discuss now? How do we go along, Yadav sir?
Dr. Swetha,
Sir?
so before we take the questions, I would like to congratulate you that you have done this complex subject in a very simple way, because you have to use a tool what we call analogies. That is a very tool which is needed for learning and teaching, and lot of innovations and other things.
Thank you so much.
Yeah, this will definitely go a long way to create interest in the microwave in general and in particular from your side.
Yes.
Thank you very much for this exposure.
Thank you so much, sir. Thank you so much.
I enjoyed every bit of it.
Hello, Namaste, madam.
Namaste, sir. Please, sir.
I am Professor Sheshaprasad from BNM Institute of Technology. It was a wonderful explanation by you, madam. Congratulations.
Thank you
You
so
made
much.
the concepts very simple, just like we were listening as though we were students again. It was really nice. Ma'am, I am doing my research on human body communication through this antenna, microstrip antenna. Can you please throw light on what are the materials that could be used for, because we can't test the antennas directly on human being. So these models that is available are very costly and which is not affordable by the researchers. So what is the simple way of testing this antenna on putting this antenna on the human body other than simulation? Because when we do simulations, I don't think we will have a valid results. So how are we going to do this on a human body? Can you please throw us light?
Sir, if you, I can just tell a glimpse of it. On Wednesday, there's a session about wearable antenna only, sir. We'll be completely talking about active wearable devices, antennas, which are exclusively used for wearable textile materials. So the best option is, since we use clothing, why don't I use cloth itself as a substrate, so that I know that, I mean, if I understand that the losses or whatever is much lesser than using a FR4 or an RT Durant, why not use textile itself as a substrate? When I will completely explain about what are the materials, how do we test it, what are the models to be used, we can completely discuss on day, sir. ಕೇಳಿದ ಮೇಲೆ we can discuss the questions, alva sir?
Yes, madam. Thank you, madam.
Thank you, sir.
Ma'am, hello.
Yeah, Diksha, tell me.
Ma'am, my name is Apurva. Ma'am, actually, I am very much interested in this topic of microstrip antennas. I'm thinking of doing my PhD in this topic. So, ma'am, could you please throw some light onto this health monitoring systems, like antenna for this? I actually was not aware of this topic. Ma'am, could you throw some light on this?
Definitely, my dear. So Wednesday's session, we will completely discuss on wearable antennas. I'll completely tell you whatever I have done so far.
Yes.
So that will give you an idea to start your research also, okay?
Okay. Ma'am, very nicely taught. I really loved the way you taught this, and it actually increased my interest in this actually.
Thank you so much, dear. That's what is the intention. But, I mean, people are scared. RF, microwave antenna, yaar, bahut zyada equations hai, tumba kashta, I cannot study. I mean, that's not a fact at all. I mean, you can enjoy this subject also. Yes, you need to know a bit of that Maxwell guy, but life is very easier with it.
Okay. Yes, ma'am. Thank you. Ma'am, are there any freely available simulation tools which we can just try, so that we get better?
You message me on my WhatsApp here, I will tell you. There are a lot of crack versions which I shouldn't be telling you this because we are told to use the licensed version.
Yes, ma'am.
But then again, you are a student, you can explore many things there.
Yes, ma'am. Yes, ma'am. I'll definitely do that. Thank you.
Okay.
Good evening, madam.
Good evening, sir.
Madam, myself, Dr. Samir Chakravarti from Visakhapatnam, Andhra Pradesh.
Yes.
A big round of applause for your efforts, madam. It's a very good lecture. In fact, however, it goes directly into the hand of student.
Thank you, sir.
Just would like to know one thing, madam. From your expertise, can you just relate the as well as the impedance? Which one do we have to actually take care of while concluding the final design of an antenna?
Okay. What is your question, sir? Impedance matching?
Impedance matching. That means impedance response as well as S11. These two curves we would like to know which one is more reliable and dependable. At a stretch, if we go for a fast sweep response of a particular antenna while designing, what would be kind of frequency response would be reliable?
Test parameters, sir. I have done 1 or 2 consultancy projects wherein the industry people ask me, let the written loss be less than minus 10 dBm. So the industry are very happy if the written loss is less than minus 6 dBm also, 6 dB also. But if it is less than minus 20 dB, that is perfectly getting equal to 50 ohms is what we can say. So SPR you can start with. We recognize less than minus 50 dB, you can work on it and make it minus 20, minus 30. And as it goes to minus infinity, your impedance will hit the 50 ohm line. So directly going on to Smith chart and finding the 50 ohm point, rather than that, you play with the S parameters. I would say S parameter would be good enough to start the analysis also.
For initial antenna engineers, madam, which type of feed do you prefer, like probe feed or the strip feed, edge feed?
Edge feeds are comfortably
Which kind
edge
of
feed as long as the width is made 50 ohms.
Okay.
Yeah.
Great, madam. Thank you very much.
And then
Kindly share your email ID. In touch. Thank you.
Sure. Definitely, sir. Definitely. Thank you so much.
Hello, ma'am. This is Vinay from ISRO.
Yes, Vinay, sir.
Yeah, it's a very good lecture, and I would like to ask you some questions regarding. The first one is you said that you will go for a rectangular type of strip line for narrowband and a circular kind of strip line for wideband. How can we physically visualize if we change the dimension from rectangular to circular? How the more number of frequencies we can receive through that antenna?
As simple as this, if I take a rectangular patch, I have 4 edges there.
Yes.
So the current which is going, hitting the edges and coming back, there is a lot of disturbance or absorption happening there. But
Yes.
when it comes to a circular one, that's not the scene, right? The current is equally going, equally coming back.
Okay.
So that's why I get a wider band with the circular one.
Okay. And can you explain about near field? Near fields, where you said that E field and H field will not be perpendicular to each other at a near field. How can we think about it? Because whenever a current is passing through a conductor, we'll get a magnetic field around it. Anyway, it will be in the perpendicular condition only. How can we say that at near field, these two are not perpendicular to each other?
Okay. How I haven't demonstrated it anywhere, but so when I'm throwing out energy, for it to align itself, it takes some distance there, sir. So the energy which it is throwing out, so the moment it's throwing out exactly a bit near to it, it's the E and H are not perpendicular. The reason it's probably because the E does there, it takes for it to radiate and having electric and magnetic field completely perpendicular to each other. So, I mean, I have not much done any research in near field. All I know is since E and H are not but once the ripples start occurring uniformly, that's when we mostly talk about all the boundary conditions, all the far field regulations and everything.
Hello, my question is that, hello.
Yeah, please tell me.
Hello, ma'am. Ma'am, how one can determine the mode of propagation of antenna?
Okay, the dominant mode as such?
Yeah.
Okay.
And one more question, the point of the 50 ohm, how one can determine this coordinate is suitable for the 50 ohm?
Okay, we do have certain equations which tells us the point where exactly the impedance hits the 50 ohm. So it's completely surrounding. So at the center, the resistance is 0. But as we move along in any given direction, I will hit a 50 ohm line. So I need not much bother in which direction I'm moving. So we have certain
Means we have
equations.
to move mechanically from here, from center to.
No, not mechanically. You can play around in simulations, or if you can share me your email ID, or I can send it to everyone. There's a very nice paper by I don't remember the author. He has given very good equation-wise analysis of how exactly to find this 50 ohm point given your substrate behavior and everything.
Okay, ma'am. Please share that paper. And
Madam,
second question for propagation of
I can
antenna.
add something in this. When we are not getting the right perfect impedance match, think about a matching circuit in between. Because it's very easy to do it.
A balloon, something.
It is easy to do it. So we need not to really worry that much. Even we hit that point, and by fabrication process, if we are not really at that point, still there will be a lot of mismatch. So it's better to think about a impedance matching network in between. So that will solve the problem automatically. We have to optimize the solution.
A simple balloon which will convert unbalance to a balanced circuit. Yes.
Excuse me, ma'am.
Yes.
Ma'am, second question, ma'am, mode of propagation, dominant mode of propagation, how
Okay.
it will be determined.
Okay. So then again,
Can I ask a question?
Slides we spoke about equation Hampstead formula, which exactly tells me that for my dominant mode T101 or whatever it is, I can how can I calculate, or how much should be this delta L what I am talking about, no? When we calculate the length of the antenna, delta L matters to me to decide so which is the dominant which I need to choose. So everything, most of it can happen in a microstrip through equations itself. So we need to know what exact equations we need to use for these things. Okay, so that's possible with equation. I'll share you those equations also.
Excuse me, ma'am. Ma'am, myself, I'm a student of Ramya Institute of Technology, ECE department, second year. Yeah. Yes, ma'am. So my question is like, I have a doubt. How do you like design an antenna? You told you need to set a frequency of operation, right? How do you do that particular thing, and how does that antenna hit a particular frequency? And is that circular rotation, right hand side circular rotation, left hand side, and linear rotation, is that involved? And which is more feasible?
Okay, so first thing is any application you choose, assuming you are designing an antenna for mobile application, you are designing for a satellite, you are designing for IoT, everything has a priority already given to it, right? Yeah? So you would know the frequency. So knowing the frequency, whether you are calculating or designing an aerial antenna or a microstrip antenna. So if it's a microstrip antenna, then you need to know whether you should choose a simple rectangular patch or should it be a circular. So then again, with the help of shape itself, you can control the polarization also. There are n number of articles, journal papers, conference papers, and IEEE papers, which says you just by controlling the shape of it, you can control the polarization also. Okay, so that's what I mean. Yeah.
Ma'am, and here shape you're talking in terms of that rectangular with that 4 edges and.
I mean, those two are very simple shapes. If I have to tell you, rectangular and circular, there are n number of slots which you put. Okay, to change the polarization.
Madam, choice of the shape is not only affecting this part of it. It can also have, can be chosen optimally for side lobe suppressions and other things. Yeah, side lobe suppressions also we can. So when we are selecting this one, it will be very nice. Yeah, it will be very nice. So selection is not.
Hello.
Basically, our circle is easy, but choosing a complex pattern also can help us further. Think about a side lobe suppressions and have other things also. Optimal energy has to be confined for the direction in which we need it. That's all we are trying to do it for optimization.
Hello.
Hello, madam.
Hello, ma'am.
Hello, I am Vidya Kojgirwar. Hello, madam.
Thank you very much for explaining this in a very
I would like to
simple
ask
language.
you one question regarding the phase array.
Ma'am, I have a doubt about the axial ratio. What is the axial ratio? Can you please explain me in the common language, like the way you explain the polarization and all the stuff?
Axial ratio directly depends on your polarization.
Anil from Kerala
Grating.
University. How to get deviant circuit, ma'am? Hello.
Hello, sir. Sorry, I didn't get you.
How to get
Yeah.
hello?
How to get? I don't know. Yeah. For a rectangular patch, I got it. Every given structure, you can have an equivalent circuit. So probably you need to learn complete transmission line, the R, L, G, and C's. And then when we put another structure like this, what would be the reactance component, resistive component? So yeah, that. If you are starting to find out what is the equivalent circuit, probably I'll tell you completely understand the transmission line, and then go on with the equivalent circuit for a simple rectangular patch antenna. Understand that, and then probably you can go with any complex antenna. Then what happens when you put a slot? What is the lump circuit which gets introduced into it? So those kind of analysis can be done.
Hello, ma'am. How grating lobes depend on the structure of patch antenna?
Grating lobes, I have not much worked on the side lobe reduction and all grating lobes also. Yeah.
Okay, ma'am. And you wrote somewhere FR4 4.3 at 1 gigahertz. What is the meaning? Like it's 4.3 values depend on frequency. Because if it is same for all.
No. Probably it was 4.4 is the dielectric constant of the material which I chose, and I designed this antenna at 2.4 gigahertz.
Okay, ma'am. Ma'am, you said that using circular pitch, we generally got the wideband. Why we didn't get the multi-resonant type property from circular pitch?
Okay. Yes. So that's again a very good question. A simple circular patch, I get a wide band. Okay. In the next session where I will be talking about wearable devices, there for a same circular antenna, I have put some slots inside it, which means I have made some holes of different shape and everything. So this has helped me in getting multi-band. So we were trying to design one antenna for both Wi-Fi frequencies. So we started with an ultra wide band and reshaped that antenna in such a way that it is giving me only 2 bands. That's also possible. Yes. So
okay, ma'am. And last question, ma'am. You said that impedance matching section 50 ohm. You discussed about the 50 ohm. Then what is the difference between 50 ohm and the free space impedance? Because it's generally 377 ohm, 37 ohm.
Okay, that is free space impedance. That is when it goes out in the air, depending upon root of mu by epsilon r, right? This impedance is see, assuming that as simple as this, I have a signal generator and a CRO. Okay, give 1 volt at the signal generator, and I see 1 volt in the CRO also, right?
Okay.
That's because the impedance of these two component equipments are matched. If it doesn't happen, what do? We do something in the CRO so that a potentiometer is changed, then impedance is matched. So this impedance is talking that it should be the same. So usually it's seen that it is 50 ohm. So antenna is also designed at 50 ohm impedance.
Okay, thanks a lot, ma'am. Thank you so much.
Hello, madam. I am working on adaptive array.
Okay.
Hello.
Okay. Yeah. Tell me, ma'am.
Okay. Yeah. Tell me, ma'am. And actually I have designed the array with microstrip antennas, microstrip patches, with 8 elements. And actually for testing of we require the different weight, means amplitude and phase shift, different phase shift. But practically for testing of this array, we require the DSP processor, some algorithms and all those, which is very complicated. Is there any simple method for testing of this array?
No, ma'am, I wouldn't know much. Phased array. All I know is steering with the phase shifter.
No,
Recently,
a simple testing of the simple single antenna element is easy.
Yeah,
Testing of single element, but testing of the array is very difficult. Actually, simultaneously we have to apply the signal with different amplitude and different phase shift. And for that, practically we require DSP processor and for generation of the that weight. I just wanted to ask whether any simple method is there, means single probe is divided into the 8 like that. Any other method?
no, Mama, I'm not much aware of it. Or I know that the phase shifter can be used. There is a special substrate which I gave. BST, barium titanium. That substrate helps me in changing some voltage level and changing the phase. I came across. I'm not much sure. You are BST substrate.
Okay. Actually, I have used only FR4 substrate for all these array elements.
Okay.
Substrate is common for my array. Substrate is common.
Set.
And I have to apply the signal with.
So, Dr. Swetha, very good lecture.
Sorry, communication broke.
Hello.
Okay, madam.
Okay, sure.
Good afternoon, ma'am.
Discussions, probably you can always feel free to mail me. I'll write down my email ID here in a chat. You can, if it's not possible to be discussed now, so probably I'll also learn. You can mail me, and whatever it is, we can have a discussion over it. Yadav sir, I think connected.
Yeah, that's right. No, I mean, due to multiple noises, we had to mute the.
I have saved complete chat, so whatever questions are posed, I'll answer them one by one and mail everyone.
Yeah, I think the remaining questions, I request all the participants, you can try to mail or in the chat window. Well, I would like to thank Dr. Swetha. It was very nice. I mean, people are really enjoying. So from the fundamentals, so it was very well narrated. So thank you very much.
Thank you so much.
Participants, you can just try to mail the questions. And for today, we'll break the session and we'll join tomorrow. Yeah, thank you all.
At 9:45 around, we will assemble. So 10 o'clock, the session starts by Madhavya sir. So he's going to talk about antenna measurement techniques. What all equipments do I need to have once I design, and how do I measure it? What all parameters I need to know? What are the measuring techniques? In a very simple way. And he's going to take up the session on that. Okay, thank you so much. Thank you everyone for patiently hearing out on me. Thank you.
Okay. Yeah. Thank you all.
Thank you, Bhatia sir.
Thank you, ma'am.
Bye, sir.
Yeah, I think what he was trying to do, the question, last question, what it came as, he is talking about mutual coupling and effects.
Okay, nice.
That is a different, slightly different domain. How do we take when it forms an array? There is a mutual coupling, another thing. That will also be by that. How do we get rid of that? Another thing. I mean, how do they, in fact, certain mutual coupling can be taken for the benefit also, not only the bad effect of that. So that is a further enhancement of that. An extension of all these things when we talk about that, being done with this one, extending towards the MIMO and MMIC as other things, will be the another area. Antenna is not only what is the different advantages will come. I think in the coming sessions or somewhere we can make a mention about those things. That will motivate, especially the researchers and the student community to get into this. Really, you have done very well. Thank you very much.
Thank you, sir. Thank you so much. Okay, sir. Thank you.
Yeah.
We'll end the session today. Thank you.
Yeah.